This is the final video for our magnetism unit, and it is over magnetic induction. Magnetic induction can be a little bit tricky, so you may want to watch this video a couple times, or even just watch it all the way through first before you try to take notes, and then watch it a second time and copy everything down, or vice versa. But you probably don't want to try to watch this video and write it down as you go along. You might get lost, but that's okay. That's why you have it as a video, so you can watch it as many times as you want. So magnetic induction is actually started by or discovered by Michael Faraday, which is a picture of him. And you heard his name before when we talked about electricity, when we talked about electric fields. And so it's the same guy that kind of discovered magnetic induction. So you can see a little picture of him with his little magnet, and he's so proud of it. So magnetic induction is basically the opposite of what we have been doing so far in class. So far in class, we've been talking about if you have a coil of wire around something that if you put current through this wire, it generates a magnetic field. And so induction is like the opposite. So induction is that you move a magnet inside and outside of this coil, and it makes a current. Instead of a current making a magnetic field, you're basically using a magnet to create a magnetic field, which then creates a current. So it is backwards of what we have been doing. So magnetic induction is basically forcing electric current by moving wires through a magnetic field, or you can move a magnet through wire loops. So this has a lot of applications for us, because that means that we can generate electricity or induce electricity if all we have is a magnet and some means of moving the magnet. So any electric generator is basically based on this principle. So anytime you see a big wind generator, or like a waterfall has a hydroelectric generator, all of these are just using magnetic induction, and it gives us nice cheap electricity. So let's look at this diagram and then kind of make some conclusions about how induction works. So in this first part, we have a magnet moving in, deflects the current deflects this ammeter one way. And remember, an ammeter is how you measure current. So when the magnet is moving in, the current flows this way. And if you jump down to the bottom, when the magnet is then being pulled out, then the current flows the opposite way. So that means that the direction of the magnetic field and how the magnetic field is changing is going to depend, or is going to change which way the current flows, which should make sense because we've been using direction a lot in this unit. But notice that when there is no movement and the magnet is just sitting in the pipe, that there is no current. So what that implies to us is that current is only induced when a magnetic field is changing. So if there is not a change or a movement in the magnetic field, there is going to be no current, only when there's a change. So the current has a very strong dependence on a magnetic field changing. So the guy that kind of really quantized this and made an equation and did a lot of calculations came up with a law, and his name is Lenz, so it's Lenz's law. And it's basically, he said that anytime a magnetic field is changing, there is a induced magnetic field that opposes that change. And so it's trying to keep the original field constant. So it's kind of like, you don't like something to be changed. And so if somebody is pulling on you and you don't want to be pulled, you're going to pull back to stay where you normally are. And so that's kind of like what magnets do. If there is a changing magnetic field, they really fight that, and so they create an opposite magnetic field against the change to keep them the way they always have been. Now, they usually don't win, so that's why it says attempts. So it tries to, but it induces this opposite magnetic field to keep the magnetic field constant against the change. So in other words, more simpler terms, it's like magnets, like many people, really dislike change, and so they try to keep the field the same against the change by creating a field that opposes and undoes the change. Okay, so this is going to make more sense when we actually look at an example. So here's a coil of wire, okay, kind of like the other pictures, and here is a magnet, the north pole of a magnet. And so if you see on your screen that the field lines of the field are going to the left of your screen. So that is what this B right here represents. This is the magnetic field of the magnet alone. But you notice that as you push the magnetic field into the solenoid, you are getting closer and closer to the pole, which means the magnetic field is getting stronger towards the left. So you are adding this change, and remember delta is a change. So you're adding a change in magnetic field that's actually making the magnetic field stronger as you push it in. Well, this coil doesn't like that. It doesn't want the magnetic field to be stronger. So it induces a magnetic field against that change. And it's going to cancel out this delta B. And what are you left with? You're just left with the normal B, which is the point. It wants to keep the magnetic field constant and the same. So Lenz's law states that it's going to induce a magnetic field against the change to keep the magnetic field constant. Well, this induced magnetic field is happening in these wires. And if you use your right hand rule, if your thumb points right on your right hand, then your fingers are curling around the front, and that's why you have this arrow, and you are inducing a current then in this coil because of this induced magnet. That's why these are both red. Okay? We call this voltage that is being induced electromotive force, or most of the time you hear the abbreviation EMF, and you use a small, or not a small, but like a cursive E for EMF. Okay, so then let's think about the other side. When you're pulling the magnet out, okay, the field is still directed this way, right? This is still a north pole, and so the magnetic field is still going left. Oh, I didn't mean to do that. The magnetic field is still going left, but as you're pulling it out, the magnetic field is getting weaker because it's farther away. So that means the change is going the opposite direction because it's trying to reduce the magnetic field. The magnetic field is getting weaker. Well, again, now that you've already put the magnet in there, it doesn't want you to make the magnetic field weaker by pulling it out. So it's going to induce a magnetic field in the opposite direction to cancel out the delta B to keep your magnetic field the same. And so if you use your right hand rule again, thumb goes left, and now your fingers are curled over the coil, and that's why your induced current is clockwise. Okay, so of course there is an equation for this. So the Lenz's law equation for a coil is this. And so this little cursive E is EMF, which is the voltage induced. And so the the units are in volts. Capital N is the number of turns in a coil. Basically, how many times did you coil the wire? Like how many times did you turn the wire around it? So that's capital N. T is the time. How fast are you pulling out the magnet? How slow are you pushing in the magnet? It's all, so it's the time change that you're talking about. Okay, and then you have a delta B, which is how much your magnetic field is changing from you pulling out the magnet or pushing the magnet. Okay, and the magnetic field is in Tesla, capital T. And then capital A is the area of your coil. So if it's like a circle normally, then what's the area of that little circle? And that's in meters squared. So here's an example. A coil of wire with an area of 0.4 meters squared and with 200 turns of wire is placed in a uniform magnetic field perpendicular to the plane of the coil. If the field changes in value from negative 0.6 Tesla to positive 0.35 Tesla in an interval of 3 seconds, what is the induced EMF of the coil? So you have a coil of wire that looks like this, okay? And that's what we would call a solenoid, right? And the area, the cross-sectional area of this region right here, this little circle's area is 0.4 meters squared, okay? And it says the number of turns is 200, which means that all these little wires wrapped up, you have wound this up 200 times. And so that's what turns means. That's the capital N. Okay? The change in magnetic field is the after minus before, right? T or B2 minus B1. So 0.35 minus negative 0.6, which means you're going to get a 0.95 Tesla for your change. And the delta t, the interval of time, is 3 seconds. And I want to know EMF. So here's my equation. Negative n delta BA divided by delta t. Okay, and I just plug in my numbers. 200 turns, a change of 0.95, the area is 0.4, and divided by 3. And so I get an EMF of negative 25.3 volts, which is a reasonable voltage to induce. Okay, so pretty straightforward. Okay, so that is the end of this video, and then we are going to talk about this more on Monday and kind of talk about applications on Wednesday and generators and electric motors. Okay, and this right here is a really cool video that I would recommend that you go watch right now, and it's actually pretty mind-blowing if you watch it, and it'll be really surprising, and it has to do with induction. So watch that, and I'll see you in class.